Okay, part 2. So we're going to go through that question now. And this is how we get to that 810. Okay, this is how I calculate it. So it says calculate the amount of heat that was transferred between the metal and the water in the previous slide. So how do I know that amount of heat? Well, I can't use the metal, right? I don't know the metal. I don't know how much, what the heat capacity of the metal is because it's unknown, right? But I know everything about the water. Okay, so the Q of the water is mass of the water times the specific heat of the water times the change in temperature of the water. So the mass of the water was 32.8 grams. The specific heat capacity is given here. We could also have looked that up. Those numbers, lots of times, like your homework is going to assume that you have to go look it up. And then the change in temperature. Remember, T final minus T initial. Final minus initial always. So the final temperature is 29.2. The initial temperature is 23.3. Okay, and now I'm just going to calculate that. So this should come out to be 810 joules. You can go ahead and check that. I'll punch it into my calculator again just to be sure, but I'm pretty sure I did this part already. Yeah, I did because we were talking through it. Now, be sure that you do that subtraction in parentheses or that's not going to come out right. Yep. So 809.6 joules. 0.7. Okay. So this is the amount of heat, amount of energy in the form of heat that the water absorbed. So that's why it's positive. When we did this calculation, it came out positive. Now, the thing that affected whether it was positive or negative was the fact that we did final minus initial. That's going to give us the correct sign. But we should know that this should be positive because the water heated up, right? So it absorbed energy. Okay? And now, without even doing a calculation, I know that the Q of the metal is negative 810 joules because I know that the Q of the surroundings is equal to, but opposite sign, the Q of the system. So if I know that the surroundings absorbed 810 joules, then I know that the system lost, that's what the negative tells me, it lost 810 joules. So this is the amount of heat, energy, but heat, energy in the form of heat that the metal lost. Okay, so this is just a basic heat calculation. We're not going to answer, I realize that's why I didn't have that question on there. We're not going to answer the more complicated, what is this metal? Because that would be, one step further. Okay, for now, I just want you to understand the basic, how to calculate heat from this equation, and really to understand this idea of transferring heat back and forth between system and surroundings. Okay, so one way that we can transfer energy. All right, the second way is going to be work. And we talked about this example in last class, but I'm so glad I had a picture in here. I didn't realize I had a picture. Should have known. All right, so this is basic image of an internal combustion engine. So this would be like a 4-cylinder engine. Okay, so you have 4 different cylinders. These things that move up and down, those are called the pistons. And inside the cylinder is where you have that chemical reaction occurring. Okay? So when the chemical reaction occurs and it creates, let me zoom back in, it creates a gas. That gas pushes up on the piston. So gas expands. and it pushes up on the piston, and that's how it does work. If you remember, if the system does work, then it should be negative. The sign should be negative. So when we go to calculate this, because I think on the next page, yep, we're going to calculate it. We should see that work is negative if the gas is doing the work, okay? So if the gas pushes on the surroundings, applies a force to the surroundings, then it should be negative. If the surroundings apply a force on the gas, we would see this if it was compressed. This is not in an internal combustion engine. This is if the gas was compressed, then the work would be positive. Okay, so the equation that we use to calculate work is negative P, pressure, times the change in volume of the gas. That's it. Now, don't forget, for like the millionth time, change should be final minus initial. So it should be the final volume minus the initial volume. That's what's going to give you the correct sign. If you do negative times the pressure and you do final minus initial, then the sign will be correct, and it will tell you, is the gas doing the work or is the gas having the work done on it? And there's actually two ways you can check this. So when we do the problem, we'll check this in a second. I also mentioned earlier about the unit atmosphere liter or liter atmosphere. That is an energy unit, and we'll have to use that with work. So here's the conversion factor that you're going to need. This is on your exam equation sheet. It's also right here for doing the problem. 101.3 joules is equal to 1 liter atmosphere liter. Okay, so we'll use that in the next problem. Okay, so let's apply this equation. So this is talking about in an engine. A cylinder within a piston expands from a volume of 1 liter, so that's V initial, to a volume of 2.5 liters, so that's V final. And the external pressure is 1 atmosphere. How much work was done by the expansion? They actually already told us that the work was being done. We already know that work should come out to be negative. How? Because number one, they say how much work was done, meaning the system did the work. So if the system did the work, that means work should be negative. It's going out of the system into the surroundings. It's pushing onto the surroundings. The other way we know this is that the gas expanded. Whenever a gas expands, it gets bigger, right? 1 liter up to 2.5 liters. That is an expansion. That is the gas doing the work. In the instance of positive work, so that's what this one up here. Oh, it says it right there. You should have gas being compressed. So the volume should decrease in that instance. Then work would be positive. That would be the surroundings doing the work on the gas, compressing the gas together. Okay, so let's go ahead and calculate this. Work of the gas is equal to negative P delta V, or negative 1 atmosphere, that's the pressure, times the change in volume. So V final, 2.5 liters, minus V initial, 1 liter, and that's it. So 2.5 minus 1 is 1.5 times negative 1. So negative 1.5 atmosphere liters. Okay, let's go ahead and convert that into joules, simply because that is a more common energy unit. So to do that, I'm going to write this as liter atmospheres because that's just more common. It doesn't matter, but So I'm going to use that conversion factor. 101.3 joules equals 1 atmosphere liter. Oh man, this is when we have not used unit conversions yet at all in this class, have we? So if you need to go review dimensional analysis, also called unit conversions, this is going to be in chapter 2, I think. It's possible it's in chapter 3 as well. But we kind of start using it in chapter 2 and moving into chapter 3 and then ultimately as stoichiometry in chapter 4. But if you are at all rusty with this, you definitely need to go back and review that. Okay? So I have liter atmospheres. I want to get to joules, which means liter atmospheres need to go on the bottom. Joules needs to go on the top. And then I look at my conversion factor and it says 101.3 joules. So I'm going to put that with the joules, 101.3 for every 1 liter atmosphere. Okay, so now I just do that calculation. Negative 1.5 times 101.3 or negative 150, it's 151.95. So looks like we had 2 sig figs up here. So technically this should be 150 joules, negative 150. Do I care if you write down negative 151.95? Of course not. But on an exam, I'm going to do it in the right number of significant figures. And so it's going to say negative 150 joules. So I don't want you to be thrown off by that. Okay. So that is the amount of work. So this is an energy. Let me do that in a different color. This is the energy that the gas transferred to the surroundings. Okay? So the gas was the system, and it gave 150 joules of energy to the surroundings. It gave it, or it transferred it through performing work. So another second example of this energy transfer between system and surroundings. All right, once you practice this one on your own, and then, so this is the point I want you to pause the video. I'm not going to pause the video. Earlier, I had to do it in 2 parts because I had to go get a kid on the bus. So I want you to go ahead and pause it, and then I'm going to work through it. But it's best for sure if you go do it yourself and then come back and watch me work through it. Okay, so pause the video now. Okay, so in this question, they give us heat and work, and they want to know what the change in energy is. The biggest thing here is you need to make sure that you have the sign correct. Okay, they give you the values. The change in energy is just heat plus work. Okay, we did that at the very beginning of Monday's lecture. But we need to know how to plug those numbers in with the correct signs. So the way we know the sign is by looking at the wording. The system loses 487 joules of heat. That means this is negative 487 joules. The system lost that heat. It left the system. So negative 487 joules plus, and then let's look at what work is. While the surroundings, key point, the surroundings does 125. So let's draw a picture of this. Here's our system. Okay. Heat is going out. And I'll even say negative 487. Let me be even more specific here because this is kind of gets people confused. The Q of the system is negative 487. Okay, let's talk about this whole thing in terms of the system because they want to know the delta E of the system. So what's the Q of the system? What's the work of the system? Okay. This one says the surroundings does 125 joules of work on the system. So what is the work of the system? The work of the surroundings, that's the thing doing the work. Okay, so the work of the surroundings, it's losing 125 joules, but the system is gaining that 125 joules. Again, they need to be the same number, opposite signs. So you can think about it in terms of the surroundings, or you can just say, what's happening to the system? Is it getting the work into it, or is it the one doing the work? In this case, it's the one getting the work done on it, 125 joules, so it should be positive. Okay, so this is our overall what's happening here. So this should be positive 125 joules. All right, so I'm just going to go ahead and take negative 487 plus 125, or negative 362 joules is our change in energy of the system. So this is good. We had lots of concept stuff on Monday, and now we've got lots of application practice on this lecture. And then hopefully that means you can jump in and do some of the homework on this chapter as well. Okay, so the last concept we need to talk about today is enthalpy. All right? So enthalpy is a special kind of heat. It is heat at constant pressure. So I want you, every time you see this H, I want you to just think heat, okay? Because all of the reactions where we think about enthalpy, we're going to be thinking about it in terms of heat. It is very specifically heat at constant pressure. Another way of saying that is that the reaction is open to the atmosphere, or it's able to change its volume and kind of exchange pressure with the surroundings that it's in. But it's most of the reactions we're thinking of. This is versus like a reaction that's happening in a reaction vessel. So like when you have a chemical plant, they're going to be performing reactions inside of a closed container that's like a very rigid, hard container that keeps the volume constant. And as a result of that, any gases that are produced are going to change the pressure in that container. And so that would not be at constant pressure. So they generally are not looking at enthalpy values in those instances because it's not applicable there. It's at constant pressure, it's at constant volume, not at constant pressure. So all of the reactions we're going to consider are ones where the system is at constant pressure. And so we're going to be looking at the enthalpy value for the heat. So why use enthalpy and not just heat? Because enthalpy is a state function. Let me see if I have that written down somewhere. No, I don't. So I'm going to write it down right here. I just want to make sure I didn't repeat myself. So enthalpy is a state function. Heat is not. Just regular old Q is not a state function. And so we can't just do final minus initial for heat. We have to go through this whole process like we did up here and calculate changes in temperature and mass and specific heat capacity for every single step. We would have to do that. This is like the hikers going up a different path on the mountain. But in the example of enthalpy, or when we're using enthalpy, enthalpy is actually a state function. So if we know the starting enthalpy and the ending enthalpy, then we can actually just do enthalpy of the products minus enthalpy. Let me not do change. The change in enthalpy of a reaction would just be enthalpy of the products minus enthalpy of the reactants. So that's why it's really useful. That's why we make this very specific set of conditions so that we can think about the enthalpy in terms of a state function think of the heat in terms of a state function so that we can calculate the value a lot more easily. Okay? Don't worry about this. Don't worry about that. Okay? Conceptually, this is an important point. We can think of, and let me erase this circle so we can see this better. We can think of enthalpy as a difference in potential energy between products and reactants. Okay, so this is what we were talking about at the very beginning. We talked about potential energy changes in a chemical reaction when we talked about breaking and forming bonds. This is really what enthalpy tells us about. In these particular set of conditions, enthalpy is the key thing to help us understand the difference in potential energy that occurs in a chemical reaction. So we're going to go back to those energy diagrams that we drew at the very beginning, but now we're going to show them in terms of a change in enthalpy. And this is really because enthalpy is it's almost equivalent to energy changes as long as we're at this particular set of conditions where we're open to the atmosphere and we're at constant volume. So maybe I'll just write that up here. Energy, let's say potential energy, is basically equivalent to the change in enthalpy at open atmosphere, meaning like an open container conditions. Okay? For our purposes, that is a fine assumption. Okay, so in this first example, this is one where we should have a negative sign. So this corresponds exactly with when we talked about changes in energy in class on Monday. We saw that if the reactants are at a higher potential energy and they go down to a lower potential energy, then the energy change should be negative. That's true of the enthalpy change too, because energy is basically equivalent to enthalpy in this instance. And if we go up in potential energy, then our enthalpy change should be positive. So same thing with the one that energy is coming out, where we're going down in potential energy. Another way of saying that is heat is coming off of the reaction or being emitted. For one where the potential energy is going up, heat is going into the reaction or being absorbed. So when we're talking about heat and enthalpy, we give these very specific names. We call a reaction like this one exothermic. So exo means like exit, thermic means heat, or heat is exiting the reaction. For an endothermic reaction, heat is being absorbed. Thermic, heat, I don't know what endo is, that some Latin thing probably, but heat is being absorbed into this reaction. So endothermic reactions, enthalpy is positive. Exothermic reactions, enthalpy is negative. Another way of summarizing that is in the case of let me see if I make this smaller. Yep. In the case of an exothermic reaction, the products are at a lower potential energy. In an endothermic reactions, the products are at a higher potential energy. We already said in an exothermic reaction, heat is being released, whereas an endothermic, heat is being absorbed. We mentioned this earlier as well. An exothermic reaction, or one where we're going to a lower potential energy, that's considered more favorable. Whereas an exothermic or an endothermic reaction is not favorable. It still can happen, but it's not favorable. And then finally, when we talk about the products being at a lower potential energy, so we're talking about exothermic reactions here, when we talk about the products being at a lower potential energy, what we mean by that is that the energy that's required to break the bonds is kind of overcome, or there's more energy that's released when the bonds form. So the bonds that form and release energy in the products is more than the energy that's required to break those bonds in the reactants. And then the reverse in the case of an endothermic reaction. So just be really clear that that in an exothermic reaction, not even just be really clear. We're going to do more examples of this. We're actually going to calculate enthalpy by looking at bond energies. So this idea of more energy being released from the products than is required when the reactants break, that's going to be emphasized when we do one of those calculations. So if you're not quite getting that, you'll see it again. Okay, now just a couple things to know when we look at enthalpy values. They're very often written just at the end of a chemical equation. So this would be called a thermochemical equation when we include the enthalpy. And this is for the whole reaction occurring, okay? You can't take one individual piece of the reaction and say what the enthalpy is. That's for the whole reaction occurring. But, as we're going to see, this works the same way as any other stoichiometry example. So if you remember from chapter 4, or if you don't, you should go review it. If 1 mole of, this is propane, if 1 mole of propane is combusted, it will make 3 moles of CO2, right? It also makes 4 moles of water. But we can think about those as an individual conversion factor, right? We can say 1 mole of propane for every 3 moles of CO2. And we could even flip that if we needed to for using it in a stoichiometry problem, however we needed to use it. Well, the cool thing about enthalpy is that we can use it in the same way. We can say that for every 1 mole of propane, we produce 2,044 kilojoules of enthalpy, or really heat energy. Okay? Produce, because it's negative. That's how I knew that it could be said as produce. Hang on one second. Okay, I'm just going to add this in now. So the other thing I want to add in is we can think about heat as being a product in this case because it is produced. Now, it'll always be written at the end, but if it's negative, keep in mind that what we're saying is that along with the CO2 and water, 244 kilojoules of heat comes off. Okay, it's like it's a product when it's negative. Okay, this is going to correspond to the number of moles too. So for this chemical reaction, that amount of heat is for 1 mole of propane. So pause the video, and I want you to see if you can figure out how much heat is produced if it was not 1 mole, but it's 3.45 moles. So you're supposed to be pausing the video now if you haven't. Now, technically, you could probably pretty quickly understand that since there's 1 mole of propane in the balanced equation, you just need to multiply negative 2,044 by 3.54. Okay, in this instance, I'm going to show you that you can do it like a conversion factor as well, just in case it gets more complicated. This is a better way to approach it. Okay, units so that they cancel, and then we look up here and say negative 2,044 for every 1 mole of propane. Okay, so 3.45 times negative 2,044, or negative 7,154 kilojoules of heat. Okay, that's the amount of heat that would be given off for 3.45 moles of propane being burned. And finally, I promise, very last thing, is that if we have a chemical reaction where we just multiply the whole chemical reaction through by a constant. So if you see in this first one, we've got carbon plus oxygen forming CO2. If we just add a 2 in front of all of those, then we would just need to multiply the enthalpy by 2 as well. Okay, that one should be pretty obvious because just like we did above, if we have 2 moles of carbon, then we're going to have to, have twice as much heat produced. It's just that we're going to think about it in terms of the overall reaction. Another interesting property is if we reverse the reaction, then the number stays the same. The sign just changes. So this actually shouldn't be that surprising. If you scroll back and look at our examples from Monday about energy change, this reaction was shown as a specific example. And it was just like, here's the this reaction, which is negative, would look like this. So the reverse reaction would just look like this. It would be the exact opposite. So in the reverse reaction, you have positive 393.5. In this reaction, you had negative 393.5. Okay, so these are things you're going to need to use as we move into the last types of calculations for this chapter. If you multiply the reaction by a coefficient, it multiplies the enthalpy by that same coefficient. If you reverse the reaction, then all you do is change the sign. And so the last example problem we're going to do for today is determine the enthalpy based on these changes. If I have this reaction, tell me what the enthalpy is for this reaction. So pause the video, think through how you can use these relationships up here to determine that. I don't know what that was. Okay, now you've unpaused it, I assume. So let's see what's different between these two. So the first thing is it's been turned around, right? The CO2 and water are now listed in the reactant side, and the C3H8 and oxygen are now listed in the product side. So we flipped it around. So that's one thing. Another thing is that it's been multiplied through by 3, right? 3 propane instead of 1. 15 oxygen instead of 5, 9 CO2 instead of 3, and 12 water instead of 4. Okay, so the whole thing has been multiplied by 3. So if I want to know what the new enthalpy is, I'm going to have to take this value. I'm going to change the sign because I flipped it around. So now it's positive 2044. And I'm going to multiply it by 3 because I multiplied all the coefficients through by 3. So the overall change in enthalpy is 6,132 kilojoules for this reaction. All right, I realized that was a lot of stuff. Like I said, I'm really sorry that we've had to do 2 days now for the 9 a.m. class at least as videos. So let's just recap what we talked about today. Let me just write down like a summary list. And I definitely at this point would want you to do the homework. So I want you to make sure to do as much of the homework as possible for chapter 7 before Friday's class, because we're going to move into new things and I need you to make sure you're comfortable with the old stuff before we move into this new stuff. So from today, we talked about state functions, just briefly what the concept of a state function is. We used this equation and this equation to figure out heat and work that can be transferred in a particular process. And remember that the change in energy is a combination of those two. Then we talked about enthalpy of a reaction, how this relates to potential energy. We talked about exo and endothermic reactions and how that relates to the sign of the enthalpy and also to the potential energy. So energy diagrams, we'll say, relating to these. And then finally, enthalpy manipulations. So manipulations with reactions. Okay, so chemical reactions where you have an enthalpy value. Okay, so if you haven't realized, this is kind of heavy stuff. So I need you guys to make sure to step it up a notch in your study habits. I know that not everybody did as well on the exam as they wanted to. So you really, really need to be taking personal initiative here. This is Chem 2. It's not Chem 1. It is definitely a step up. And you need to make sure that you are studying. You know, you should be putting in, you didn't have to probably do a whole lot of studying between Monday's class and today's class. So you should anticipate studying maybe 2, maybe even 3 hours between now and Friday's class. You need to cover the first half of chapter 7. If that means reviewing these notes, that's great, but not just that, because you need to hear me explaining it, but you also need a second way of hearing it explained. So watching the videos again, reading the textbook, and then you need to actually practice what you've read and understood so that you know, do I know how to do something with this information? So that's where the homework comes into play. So you should be able to do about half of the homework, I would say, maybe a little bit less than half, but about half the homework, and get that done before Friday so that when we get into Friday and start doing more complicated things with that stuff, that you're not stuck on, oh, I don't remember how to do Q equals MC delta T. I didn't practice that at all. You need to practice it so that you feel comfortable coming into class on Friday. Okay, please email me with questions, even if it's like a homework question that you don't get and you want me to work that as an example. I can definitely do that. Like I can make a quick video and send it out to everyone. But you know, I'm around today. Like I made this video. I'm sitting here with a sick kid. I'm a little bit under the weather as well. But I'm happy to answer emails, make videos, whatever I need to do to make sure you guys are on top of this, okay? So do your own studying so that you know what questions to ask and then come back and ask those questions, okay? I'll see you guys on Friday.